All right, everybody. So today we're looking at composition of functions, but more specifically, the domains of composition of functions. So in order to talk about those, we first need to define what the domain is. The domain is all possible x values of a relation. So all possible x values of a relation is the domain of that relation. How can we determine the domain? There's more or less two different ways to determine, right? The first method would be look at the graph, right? So you look at the graph and you determine what x values is that graph never going to hit. The second way to determine domain, if there is no graph, you have to ask yourself, what x values can I not plug into this function? So that's the other way. So what x values cannot get plugged in to this function, or to the function? All right. So define domain, all possible x values of a relation. How to determine the domain? Either you look at the graph and you determine what x values does the graph not hit, or two, you say what x values cannot get plugged into this function, into the function. Or relation if it's just a relation. So examples of domains with graph. As you can see, this graph is going to the right forever, it's also going to the left forever, and then all of these points in the middle are getting covered. This is our standard domain that we have talked about a million times. We call it all real numbers. We also can just use the symbol, the double bar R. This next domain right here, number 2, it actually stops right here on the far left, also stops on the far right at this point, and then we just need to determine those values. So 1, 2, 3, 4, 5, so that's negative 5. 1, 2, 3, 4, 5, 6, 7 makes that positive 7. Both of those were closed circles, so they're included. So this graph is going from negative 5, from negative 5 to positive 7. And whenever the values are included, meaning closed circles, we would put brackets around that. Oh yeah, we need to discuss one more way to talk about all real numbers. Some people might still like the negative infinity to positive infinity. It's a great way to write all real numbers as well. All right, this next one. So as you can see, this graph is starting at this point and then going to the right forever, basically. So then we have some point furthest to the left, which that is negative 1, 2, 3, and it's included, it's a closed circle, so we have negative 3. And then we're going to the right forever, which would be into positive infinity in the x direction. So that's how you would determine a domain graphically. The more confusing one is to determine the domain just based off of the function. All right, so there's two big functions that are going to show up in this class that restrict the domain. The first one is when we have x in a denominator. So we have 1 over x. The problem with these, you cannot get 0. So you cannot get 0 in a denominator. So that's the problem with these kind of equations. And like you're going to see them, they're going to look like this. So we'll be like 2 over 2x plus 5. Or maybe you could have 4x divided by 3x squared plus 1. These are all instances where there's x's in the bottom, which could lead to you getting 0 in the denominator. I guess this is a bad example. Let's say 3x minus 1. Okay. So 3x squared minus 1. So both examples where you could end up with x's in the denominator, which cannot happen. All right, so that's going to restrict the domain. And it's going to restrict what numbers we're allowed to plug into that equation. The other thing is when you have square roots or fourth roots, so like the square root of x, fourth root of x, you cannot get negative numbers. You cannot have negative numbers in even roots, right? So no even roots can have a negative number because that would give us an imaginary number. We can't graph imaginary numbers in the real axis. And then our examples of this would be like fourth root of x plus 2, sure. Or you could have the square root of x minus 7, right? Those would be just some examples of equations where the domain is going to get restricted because we have to make sure there's no negative numbers. All right. So how do we determine the domain of functions like these? Number 4 here. So we're looking at number 4. We're looking for our two types of reasons that bring restrictions. One is there is an x in a denominator. The other is there an even root present in the equation? So for number 4, there's no x's in the denominator. Also, there's no even roots present. So then there are no restrictions. We can plug any number we want into both of these x's. So then our domain, all real numbers. Or you can say negative infinity to infinity. All right, number 5. Number 5, we have an even root that shows up. So let's talk about how to do these ones. We can't have negative numbers inside of the root. So that means x minus 2 has to be greater than or equal to 0. That's how you're going to determine the domain for this function. So we add 2 to both sides. You get x has to be greater than or equal to 2. So that tells us that the domain is bracket 2 to positive infinity. And that would be the domain. Okay? And let's think about that, right? You plug in 2, you would get the square root of 0, which is perfectly fine. But as soon as you go smaller than 2, you go 1.99999, you're going to get the square root of negative 0.00001, right? That's still a negative inside of the square root, okay? You can't get that. So then anything smaller than 2 doesn't work. Okay? Number 6, the restriction here is we now have a fraction. Specifically, we have an x in the bottom, right here. What's true about when there's x's in the bottom? That denominator cannot be equal to 0. So we need to say x minus 3 cannot be equal to 0. So we add the 3 to both sides. That tells us that x cannot be equal to 3. All right, well, there's only one restriction. X just can't be equal to 3. So how do we write the domain for that? Well, we say we're going from negative infinity all the way up to 3, but we can't be 3, so we put a parenthesis there. And then we say it's union with 3 all the way to positive infinity. And so this domain is telling us we're literally just jumping over that point that is 3. And that should make sense, right? You plug 3 into this equation. 3 minus 3 is 0. We can't divide by 0, right? Sorry about the dog there, guys. Number 7, same idea. We have an x in the denominator, so we say 3x plus 2 cannot be equal to 0 because we can't have 0 in a denominator. Subtract the 2, you get 3x cannot be negative 2. Divide by 3, you get x cannot be negative 2/3. So then how do we write this domain? Just like the last one, from negative infinity to negative 2/3, parentheses union, negative 2/3 to infinity. All right? And that's because we need to jump over negative 2/3. We can't have that as a number. As soon as you plug in negative 2/3, right, you're going to get negative 2 plus 2. And that's just 0. We can't divide by 0. All right, moving on to operations of functions. We add, subtract, multiply, and divide. It's also important to write the domain of these functions. So we have f of x is 3x to the 1/3. G of x is 2x to the 1/3. So when we're doing this, we're saying f of x plus g of x would be 3x to the 1/3 plus 2x to the 1/3. When you do this, the x's are exactly the same. It's both just an x and it's raised to the 1/3. So what we can do here is we're allowed to add these. That's based off of our combining radical rules. So 3 plus 2 gives us 5x to the 1/3. Thinking about the domain of this function, are there any restrictions, right? If we say 5 cube root of x, cube root is not an even root. Therefore, we could plug positives, we can plug negatives into this. It doesn't matter. So we can really plug in all real numbers, right? Negative infinity to infinity, or all real numbers, however you want to write that. For number 9, we have f of x minus g of x. So that's 3x to the 1/3 minus, and then that is going to be 2x to the 1/3. This 3 minus 2 would just give us x to the 1/3. And again, cube root, we're allowed to plug whatever number. So we just get all real numbers there. Number 10, f of x times g of x. So let's take a look at this one. This is 3x to the 1/3 multiplied by 2x to the 1/3. So what's happening here? Again, it might be easier to write these as their cube roots just based off of, sometimes cube roots are easier to use than than fractions, or you can just remember that when you multiply the same x, when you multiply the same base, their exponents get added. So we have 3 times 2 in the front, we have x times 1/3 plus that 1/3. So we get 6x to the 2/3, right? Again, this is only a cube root. There's no restrictions when plugging in a cube root or plugging x values into a cube root. So when we're just going to say all real numbers again here for the domain. You're allowed to plug in any positive number you want. You're allowed to plug in any negative number that you want, so there's no restrictions. So all real numbers. F of x divided by g of x. So here we have 3x to the 1/3 divided by 2x to the 1/3. In this case, we go 1/3 minus 1/3. So this is really 3 halves x to the 1/3 minus 1/3. Well, that just becomes 3 halves x to the 0. X to the 0 is just 1. So this is really 3 halves times 1. Or you can just say, right, that's just 3 halves. Okay, so that's it simplified. But the domain of this function is kind of weird, right? The reason being is because of this x at the beginning of the simplification process. That x in the denominator affects what the domain of the function at the end is. Okay? We're not allowed to plug in 0 into this equation, because if you would plug 0 in right here, you would get 2 times 0 raised to the 1/3. 0 to the 1/3 is 0. 2 times 0 is just 0. We cannot divide by 0. So the domain of this function is from negative infinity to 0 union 0 to infinity. If you weren't sure what number was going to make 0 in that denominator, remember you can go 2x to the 1/3 equals 0. Divide both sides by 2. X to the 1/3 equals 0. Cube both sides to get x is equal to 0. Right, there's the restriction. Okay, so that's working with domains when we have when we're just doing a function operation. Let's take a look at a couple more of those. So in this case, we have f of x plus g of x, so that's negative 2 x to the 1/2 plus g of x, which is just going to be x to the 1/2. So we do the negative 2 plus the 1 that's here, so that's negative x to the 1/2. We can't plug negative numbers into that equation. We couldn't plug in 0, though, so we say 0 to positive infinity, right? Because this is the same thing as negative square root of x. We can't plug in anything smaller than 0 into a square root. Next up, we have f of x minus g of x, so that's negative 2 x to the 1/2 minus x to the 1/2, so that's negative 3 x to the 1/2. Again, can't plug 0 or can't plug any negative numbers into that x. So we're going from 0 to positive infinity once again. 14, we have negative 2 x to the 1/2 multiplied by x to the 1/2. So we have negative 2 times 1, which just gives us negative 2, x to the 1/2 plus 1/2 in the top, so that's just negative 2 multiplied by x. This equation right here has no restrictions, but in the original equation, before we simplified, we did have restrictions, and we always have to keep those in mind, right? Those restrictions at the beginning were that our x had to be greater than or equal to 0. At the end, x could be anything, but the restriction at the beginning takes charge. So in the end, this is really just 0 to positive infinity, okay? What does this graph look like? This graph looks like the graph negative 2x, all right? But it just starts at 0 and goes to positive infinity. So we have our coordinate plane, and then it literally just does this. It's just the right side of that graph, okay? So kind of crazy, I know, right? But the restriction at the beginning trumps the no restriction at the end, okay? If you are not sure, okay, or you're kind of confused by that, go ahead and plug this equation into your graphing calculator, into y1, see what comes out, okay? It should look exactly like this graph, all right? 15. So 15, we have f of x, which is that negative 2 x to the 1/2, and we're dividing it by x to the 1/2. So here we have 1/2 minus 1/2, which that's going to give us 0, so that's negative 2 x to the 0. So this final equation is just negative 2, all right? The problem here is we have two restrictions. The first restriction being we have a square root. The second restriction being we have an x in the bottom. Square root tells us our x's have to be greater than or equal to 0. This just x in the bottom tells us x cannot equal 0. We know that it's 0 because if you did x to the 1/2 equal to 0, square both sides, you get x is equal to 0, and that's what we can't have, all right? So we combine the two domains. X is greater than or equal to 0 combined with x cannot be 0 tells us that we need everything that's 0 or greater, but that parenthesis tells us we're not including 0. All right? So I know these notes might be starting to get a little confusing. All right? Feel free to come to office hours, come to Canvas, or message me on Canvas if it's really just not clicking at all with you guys. I would love to talk with you more about these types of questions. Okay, next up, composition of functions. So you should have done these in the past, all right? And what a composition of function is we're just plugging one function into another function. So plugging one function in for x into another function. So that's what a composition of function is. We're literally taking an entire function and then plugging that in for the x of another function. The domains get kind of wild with these ones. Just like in 14 and 15, where we had to consider multiple domains, same thing happens in these compositions of functions. All right? Oh, you might be wondering what the graph of 15 looks like, guys. It's literally the horizontal line at negative 2, and it's just going to the right. Okay? And actually, I shouldn't have drawn a closed circle because your graph would have an open circle right there. In a graphing calculator, it's not going to be an open circle. It's just not, you won't even be able to click to the left anymore once you get to 0. It won't say anything. All right? So go ahead and try to graph that one in your calculator too. It'd be good to see what that looks like. And you always have to graph the original function. So that negative 2 x to the 1/2 divided by x to the 1/2. All right, so we're going to go new operation here, composition of functions. So we're plugging g of x into f of x. So we're literally taking this g of x equation, x plus 1, and we're going to plug it into the x for f of x. That's exactly what this is saying, right? Normally it would just be f of x, but instead of x, we have this equation, g of x. So we're replacing x with g of x. So then we're literally saying f of g of x is equal to, and then we have x plus 1 raised to the negative 1. Simplify that equation. That's really just 1 over x plus 1. All right, so we're just doing the compositions right now. We'll talk about the domains in a minute here. G of f of x would tell us that we're taking the equation for f of x now, and we're going to plug that into the x for g of x. So g of f of x is equal to x to the negative 1 plus 1. Simplify that just a little bit. You get 1 over x plus 1. There's our function. All right. 18 says f of x. These ones are conceptually a little bit harder to understand, but we know that f of x is equal to x to the negative 1. So we're plugging in x to the negative 1 into this x. So f of x is equal to x to the negative 1. That's what we're plugging in, and we're plugging it into f, which is just an x raised to the negative 1. Okay, so imagine that, right, just f of x would be f of x right here, but then we're plugging in this f of x, which is literally x to the negative 1, in for this x. Okay, simplify this equation. Negative 1 times negative 1 gives us just x to the positive 1. Okay. Number 19, f of g of 3. This is telling us plug 3 into g, and then plug whatever number that is into f. Okay, so I like to go, this is what I like to do for these ones. G of 3 is equal to 3 plus 1, so that's 4. So then I'm taking 4 and I'm plugging that into f. So f of 4 is equal to 4 to the negative 1, which is 1/4. All right, and there's our answer for number 19. You could also just do all of that in one, right? You could say f of g of 3 is equal to 3 plus 1 raised to the negative 1, okay? Versus doing it the way that I did, where I found g of 3 and then I plugged g of 3 into f, okay? So that's composition of functions. Hopefully not too bad. I actually don't remember if you guys have supposed to have done that before or not, but if not, welcome to composition of functions. So the domain of a composition of function, let's talk about what that is. So that is the intersection of the two domains of the functions. So the intersection, we're going to say the intersection of the domains of both functions. Okay. So the example here that we're going to use is f of g of x. You first have to consider, so first consider the domain of g of x. That's the first most important thing. Second, you consider the domain of f of g of x. All right? And then wherever these two intersect, that's your final domain. All right? And we're going to do a couple of examples right here. Number 20 says find f of g of x and its domain. So we're taking g of x and we're plugging it in to the x and f, right? So literally just right here. So f of g of x is equal to 2 times 3x plus 4 raised to the negative 1, right? Our first domain, g of x, right, this is just all real numbers. 3x plus 4, you could plug any number into that. So there's no restrictions there. Now we need to simplify f of g of x to see if any restrictions pop up. So this is going to be 2 multiplied by 1 over 3x plus 4. So we can really just say 2 over 3x plus 4. Yes, right? A domain restriction did pop up. 3x plus 4 cannot equal 0. So that means 3x cannot equal negative 4, which means that x cannot equal negative 4/3. So then in our domain, the intersection between all real numbers and x not equaling negative 4/3 is literally every number but negative 4/3. So we go negative infinity to negative 4/3, union negative 4/3 to positive infinity. Boom. 21. Find a g of f of x and its domain. So this time it's saying we're plugging in this equation into the x of g. So g of f of x is equal to the square root of x minus 7. That's then squared plus 4. We first consider the domain of f of x, right? This domain is telling us that x minus 7 has to be greater than or equal to 0. So that means x is greater than or equal to 7. We now can go through and find g of f of x, and we can say squared cancels with square root. You get x minus 7 plus 4. Negative 7 plus 4 gives us x minus 3. So there are no restrictions here. This is technically all real numbers. But there is this restriction from the beginning. X has to be greater than or equal to 7. So the intersection of all real numbers and greater than or equal to 7 would be all the numbers that are greater than or equal to 7. So we go 7 to positive infinity. And there's that graph. There's that domain. The graph of this function, right, is going to look like this. We're at negative 3, but then we can't start until we get to 7. So 1, 2, 3, 4, 5, 6, 7. Okay, so we're going to go up 1, right 1, 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 up 1, right 1. So it's literally going to start right here and then just go up and to the right. That's what that function would look like. Okay, so domains of compositions, domains of operations of functions, this stuff is kind of tricky. Please, please, please message me with any questions that you have. I would love to try to clear up the muddy water, answer questions about homework. Just let me know, all right? I hope you guys have a great day, and I will see you soon.